Hi, I'm Kevin, and I'm a geek. I really like working on mathematical problems and explaining them to people. I've retired from a job at a big industrial research lab where a lot of my work consisted of just that. Now that I'm on my own for a while, I'm looking for whether I can get the same sort of fun out of explaining things in videos. A lot of what I've done involves various aspects of geometry, but I'm likely to stray far and wide because the field of mathematics is all connected. In this video series, we've been examining the properties of the cardioid, one of my favorite mathematical figures. In this final episode, we'll take a look at the cardioid that is embedded in the Mandelbrot set. I imagine that anyone who takes an interest in these videos is likely already familiar with the Mandelbrot set, but I should probably take a few moments to review its definition and basic properties. The set is defined over complex numbers C by a simple algorithm. Set a number C to 0, and then iterate, replacing Z with Z squared plus C repeatedly. The set describes the ultimate fate as the iteration proceeds endlessly. If Z eventually goes off to infinity, the complex number C is not in the set. If Z stays finite forever, the number C is in the set. The usual visualization shows one color for numbers in the set, and then has a palette of other colors describing how fast the rest of the values of C shoot off. Even the main body of the set conceals subtleties. The YouTube user Mythologer did a terrific video on this, which I highly recommend. Look in the description for a link. To understand where all this complexity comes from, let's first consider what happens to the iteration for just the real numbers. That is, the ones on the horizontal axis in the picture. We'll use a visualization technique that's common for analyzing dynamic systems, called the spider diagram. We'll plot the function x squared plus c that we intend to apply repeatedly. And we'll draw a diagonal line representing the identity function y equals x. As the first step, we plot the initial value of x and draw a vertical line connecting it to the corresponding value of y. Since the initial value of x is 0, this line lies on the y-axis. The next step is to set the new value of x to the current value of y. We can do this by drawing a horizontal line over to the line y equals x. From this new value of x, we can draw a vertical line to show the new value of y, and another horizontal line to the y equals x line. We can carry out this process repeatedly to see what the limiting behavior is. For this particular value of c, the process converges to a limit called a fixed point. Now let's look at what happens when we choose a larger range of values for c. We need to zoom out to show all the sorts of behavior that can happen. Once again, we need the y equals x line and the parabola y equals x squared plus c. And we will be drawing the spider web that tracks the iteration. There's a certain range of y that converge directly to a value. That value is called a fixed point, and for it to be the ultimate limit, obviously the iterated function at that point must return its argument. As we move to larger values of c, the parabola no longer intersects the y equals x line. There is no fixed point, and the iteration shoots off to infinity. As we move to negative c, we see another phenomenon. Replacing x with x squared plus c overshoots the fixed point, and so the iteration approaches the fixed point by alternating between values that are too high and values that are too low. With larger negative c, the process appears not to converge on the fixed point. In fact, we can see why. The overshoot is so great that if we start near the fixed point but not exactly on it, the iteration moves so far past it that successive iterations get farther and farther away from it. The yellow spiderweb lines show this divergence happening as the values spiral outward from the fixed point. We call a fixed point where the iteration converges attracting, and one where it diverges repelling. If you know a little calculus, you can work out what the overshoot is for points close to the fixed point and show that a fixed point is attracting only if the slope of the function at the fixed point is between -1 and 1. For a repelling fixed point, the behavior gets quite complex. We can find one realm where it appears to converge to a cycle that alternates between two values, another one where it cycles among 4 different values, yet another one where it cycles among 8 different values, and for much of the range, there's chaotic behavior that's difficult to describe. Even in the chaos, there are islands of order. We can see cycles of period 3, period 5, and so on emerge. Each stable cycle corresponds to a fixed point of the function iterated a certain number of times. Finally, once c is less than -2, there's no stable cycle possible, and the value shoots off to infinity again. The values of c, where the behavior is simple convergence to a single fixed point, are the ones that are at most 1/4, because above that there is no fixed point, and at least -3/4, because below that the fixed point is repelling, not attracting. We've seen that there is a lot of complexity in the behavior of the iteration, even for real numbers. Now let's move on to complex numbers. I'll zoom back in a little for clarity. A spider diagram would have 4 dimensions, and I'm afraid that I don't have that many dimensions on the screen, so I'll simply plot the successive values of z. As we explore this iteration, we see that there are places where z appears to shoot off to infinity, ones where it settles to a fixed point, and ones where it appears to converge on a cycle. The different round regions, called bulbs, appear to correspond to different periods. There are ones of order 3, order 4, order 5, and so on. The patterns of the cycles can get quite complicated. The big shape that looks to be a cardioid seems to be the region where there is a single fixed point. And indeed, it intersects the real axis at -3/4 and 1/4, which we already saw as the boundary for convergence to a fixed point on the real axis. In fact, we can prove that the shape is a cardioid and show what its dimensions are. We already know that at an attracting fixed point, the derivative of the function cannot have an absolute value greater than 1. This is still true of attracting fixed points in the complex plane. I'm going to ask you to accept that for the moment, rather than going down the rabbit hole of complex analysis. In other words, the fixed point must lie inside a circle of radius 1/2 centered on the origin. Let's follow the boundary of the circle. I'll write the boundary of this region in polar form, and then move to the other chalkboard for a moment. What values of c will correspond to fixed points on the boundary of the circle? Answering that question, plus a moment of thought, will give us the values of whose fixed points lie inside and outside. We'll begin with the equation for the fixed point and isolate c on the left-hand side. Now we substitute in the formula for z on the circle's circumference and simplify the resulting equation on algebra autopilot. You'll see in just a moment why I chose this specific form to leave the equation in. Let me copy this equation back to the other board again. We can do a quick check on our work by plotting this equation on the picture of the Mandelbrot set. And when we look at its form, we see that the white line is a familiar equation of the cardioid that we derived way back in the second episode of the series. And so we've shown that there is a cardioid in the Mandelbrot set, and that every point inside the cardioid converges to a fixed point inside the yellow circle, and that every point outside the cardioid does something other than converge to a single fixed point. It's not too difficult to use the same kind of reasoning to show that the red circle, which is of radius 1/4 centered on the point -1, contains the points that converge to a cycle of period 2, and that it is indeed a circle. These two regularities are so compelling that I've seen other people assert on YouTube that the Mandelbrot set has cardioids and circles all the way down. It's particularly tempting to make that conjecture once you've experimented with magnifying the halo of the set and realize that it consists of what appear to be miniature copies of the set itself connected by filaments. Unfortunately, we discover the conjecture is false. The Mandelbrot set is self-similar in a more abstract sense, but the copies are not exact. They're described by higher-order polynomials. If we zoom into a different location, we discover that the copies can be bent and weirdly distorted. See how much bigger the left limb of the supposed cardioid is than the right? And with this very cursory look at the Mandelbrot set, I'm going to bring this series on the cardioid to a close. Next time, I'll be back with an entirely different mathematical musing. Until then, stay healthy, stay safe, and keep calculating.